Welcome, this is 48K video 2, and now we're going to start talking about collisions. So it turns out there's two basic types of collision. There's so-called inelastic collisions, and these are collisions where kinetic energy is not conserved. So there's energy escaping the system, often as heat, sometimes as sound, etc. When you're in a car crash and you hear the bang, that's energy escaping the system. When you clap your hands together and you hear the slap, that's energy escaping the system. Then there's other collisions where energy does not escape the system, and these are special type of collisions. These are called elastic, and those are approximated by pool balls colliding. There's only a tiny sound when pool balls collide. Air molecules colliding, they would be elastic. Electrostatic particles, an electron colliding with another electron, that would be an elastic collision, etc. So in the inelastic collisions, because kinetic energy is not conserved, the only thing that is conserved is momentum. You can always rely upon MOM, momentum. And in elastic collisions, both kinetic energy and momentum are conserved. We divide inelastic collisions into two kinds. There's the standard kind where one particle hits another particle, and we can compare the sum of their momenta before the collision with the sum of their momenta after the collision. And then we have a special case, and it's called perfectly inelastic collisions. And these are where the two particles stay together after the collision. So that would be like a tackle where two particles become one. Or alternatively, for example, an explosion where one particle breaks up into two. That would also be a perfectly inelastic collision. So some new terms: inelastic collision, perfectly inelastic collision, and elastic collision. So you should know those terms, and if I were to describe a collision, you could name it, or if I give you a name, you could give me a description of it. And then secondly, you got to know that with the inelastic collisions, only momentum is conserved. And with the elastic collisions, both momentum and kinetic energy is conserved. Now, it turns out if you try to do an elastic collision calculation, the chances are you're going to be given two unknowns. Two equations means I can give you two unknowns. And if you try to do a calculation using mv for the momentum and a half mv squared for the kinetic energy, that second equation, in combining with the first equation, gives you a complicated answer. So there's a true but not obvious simplifying equation. And that is this equation at the bottom, which says that the difference in the velocities before the collision is equal to the negative of the difference in the velocities after the collision. And rather than using a half mv squared and a half mv squared and a half mv squared and a half mv squared, I use v1 initial minus v2 initial equals minus v1 final minus v2 final, and life gets much simpler. So a bright person who doesn't study the materials would not know to use that equation. Hence, it's always good to look at the materials. Let's do some examples of these. So in this first example, a 7 kilogram particle with a velocity of plus 4 meters per second collides with a 2 kilogram particle that has a velocity of minus 3 meters per second, and its inelastic, so only momentum is conserved. And it says after the collision, the 7 kilogram particle has a velocity of plus 2 meters per second. And it's asking what is the velocity of the 2 kilogram particle. So the 7 starts off at 4 meters per second going to the right, and after the collision it's only doing 2 meters per second to the right. And the 2 kilogram particle, which begins going to the left at 3 meters per second, has a different velocity afterwards, and we need to find what it is. And what we say is that the momentum initial equals the momentum final, because momentum is conserved. And so I say m1 v1 initial plus m2 v2 initial is equal to m1 v1 final plus m2 v2 final. And as with all things, if there's one unknown, I only need one equation, but I've got to give you everything else. It's not magic. So I say 7 times plus 4, signs matter, plus 2 times minus 3 is equal to 7 times plus 2 added to 2 times, well, I don't know the sign of this, I'm just going to call it v2 final. So I say 28, positive 28, added to minus 6 is equal to 14 added to 2 v2 finals. So v2 final will equal, well, it's going to be 28 minus 6 is 22 minus 14 divided by 2. So v2 final will equal 8 over 2, which equals plus 4 meters per second. So this thing goes careering off to the right at 4 meters per second. So this is how they go. That's a inelastic collision. We can do these with IJK, of course. 4 kilogram particle with a certain velocity collides with a 2 kilogram particle with a different velocity. And what is the velocity of the combined mass? After the particles have a perfectly inelastic collision. So I'm actually doing an inelastic particle here, but I'm doing it in IJK. So here's my V final. So these two particles collide and they form a combination, and so it's a perfectly inelastic collision. I can say m1 v1 initial plus m2 v2 initial is equal to, and it's going to be m1 plus m2 v final. Now I'm playing with IJKs, so I can say IJK and I want m1 v1 initial. So this is this 4 times this guy, which is 8i, 4 3s are 12, 12j, 4 4s are 16. So I took the mass of the first particle times its initial velocity, and then I have to add on to that m2v2 initial, which is the mass of the second particle times the second velocity. 2 2s are 4. 2 times minus 4 is minus 8. 2 times 2 is 4. And I got to add these together. So that's going to be 12. That's going to be 4. And that's going to be 20. And then VF is equal to that answer divided by the combined mass, which is 4 and 2 makes 6. So now I need to do the division by M1 plus M2, which is 2 and 4 makes 6. So this is that divided by 6. And that gives me V final. Running out of space here. V final is equal to, we're going to have 2I plus 4 over 6 is 0.67J, and then we're going to have 20 over 6, which would be plus 3.33K, and this is going to be meters per second. Bit of a squeeze getting it in. I've just changed the layout so I have more on a page, and it is a little bit of a squeeze getting it in. So there we have it. Let's have a look at this next question. A 3 kilogram particle with a velocity of 3 meters collides perfectly inelastically. So here's another one perfectly inelastically. So this is 3 kilogram with a velocity of plus 3 meters per second collides perfectly inelastically with a 2 kilogram particle with a velocity of minus 4 meters per second. That's in that direction. What is the velocity of the combined particle after collision? So this is going to be 3, 2, and we'll just call it velocity. Now, M1 initial, M1 times V1 initial plus M2 times V2 initial is equal to M1 plus M2 times V final. So 3 times plus 3 added to 2 times minus 4 is equal to, and I like to write them down so that I am clear that I did write them correctly and add them correctly. I try not to do that in my head. Plus 9 added to minus 8 is equal to 5V. 1 is equal to 5V. V is equal to 1 over 5, which equals plus 0.2 meters per second. So what this is saying is that this combined mass will go to the right, but it'll go very slowly to the right. Now, just a word of warning here. Once I tell you it's perfectly inelastic, I could ask you for the velocity of the combination, which I did here, combined particle. I could be cunning and I could ask you for the velocity of the 3 kilogram particle because it's going at this speed clearly. Or I could ask you for the velocity of the 2 kilogram particle and check whether you understand what perfectly inelastic means. So don't rely on the fact that every time you do a perfectly inelastic, I will ask you what is the velocity of the combined mass. There's some vocabulary issues we have to learn as well, so watch out for that. So let's have a look at this next problem. We have a 2 kilogram particle which has a velocity of 5 meters per second, and we have a 4 kilogram particle that has a velocity of minus 3 meters per second, and these collide elastically, so they don't stick together, so they're going to be independent and they're going to be separated, and I want to know the velocity of the 2 kilogram particle, so that's what I want to find. Let's call that V1, and we do need to represent this second one, which is V2. Okay, so the first thing I can say is that the momentum initial equals the momentum final, so I can say 2 times plus 5 added to 4 times minus 3 is equal to 2 times v1 plus 4 times v2. So to simplify a little bit, that's going to be 10 added to minus 12 is equal to 2v1 plus 4v2. So minus 2 is equal to 2v1 plus 4v2. Okay, one equation, two unknowns. I'm going to have to do a bit more work. So I say, oh, but I also know the differences in the velocities before v1 initial minus v2 initial is equal to the negative of the difference in the velocities after. So it's minus v1 final minus v2 final. So now looking at my diagram, I see that I have 5, positive 5, minus, that's a negative 3, so it's subtraction of a negative, minus minus 3, signs do matter, equals minus, and this v1 final is going to be v1 and v2 final minus v2. Let's just rearrange this a bit. 5 minus minus 3 is 8 is equal to, let's change these signs. So that's going to be v2 minus v1. Yeah, minus minus makes plus for v2. Now the question is, which do I want? I want to find what is the velocity of the 2 kilogram one. I want to find v1. And the best way to do this is you isolate v2 in one of them and then substitute. So let's say v2 is equal to 8 plus v1. And then we're going to basically substitute that up here. And we're going to come down here. And we're going to go minus 2 is equal to 2v1 plus 4. Well, not v2, it's going to be 8 plus v1. So minus 2 is going to equal 2v1 plus 3 8s are 24, 4 8s are 32, plus 4v1. Take the 32 to the other side, minus 34 is equal to 6v1. So v1 is equal to minus 34 over 6, which equals minus 5.67 meters per second. So I'm saying that particle, that 2 kilogram particle, is moving to the left, and it's moving to the left at minus 5.67 meters per second. So there was a collision and it recoiled backwards. So there we have it. We can have an inelastic collision, we can have a perfectly inelastic collision, we can have an elastic collision, and certainly with the perfectly inelastic or the inelastic, I could do it in IJK form. I wouldn't do IJK form on this last example because it just gets too long. So there we have it.